multidimensional spaces, the exact calculation of the symbol error rate is only possible in very few cases. When it is not possible, approximations or bounds of the probability of error are useful. We'll discuss this in this video. If we have an M80 constellation in a multidimensional space, it is only possible to compute the probability of error if we have the decision regions in a grid. And we can obtain the calculation if the grid is aligned with the axes, with Q0 and Q1, like in this example here. This can be extended for constellations where we have the decision regions in a grid, but they are not aligned with the axis, because in these cases it is possible to introduce a change of coordinates to modify the constellation and to get the decision regions aligned with the axis. In this example here, it is only necessary to introduce a 45 degrees rotation in this constellation to get this equivalent one, where the decision regions are in a grid that is aligned with the axis. And it is possible now to compute the probability of error. However, if we have constellations like this one, where the decision regions are not in a grid, in general, it is not possible to compute the exact probability of error, because it is not possible to obtain the exact integral of a Gaussian out of a decision region like this one. In these cases, the calculation of the probability of error can be obtained by means of numerical calculation, numerical computation using computers. And analytical results can only provide approximations or bounds of the probability of error. Approximations of the probability of error are useful in this situation, when the calculation of the exact probability of error is not possible or is difficult. The main idea in these approximations is that the probability of error in general depends on the distances between symbols, and the most likely errors happen with symbols at minimum distance of the transmitted symbol. If we transmit a given symbol and an erroneous decision happens, in most of the cases the decided symbol is a symbol at minimum distance of the transmitted one. Taking this into account, the most common approximation approximates the probability of error as a number k, which is the maximum number of symbols at minimum distance of another one in the constellation, times Q function evaluated at half of the minimum distance between symbols in the constellation divided by a square root of n0 halves. This is assuming that the most likely situation is to have errors with symbol at minimum distance of the transmitted symbol. Q of half of the minimum distance divided by a square root of n0 halves is analyzing the probability of having an error with a symbol at minimum distance, and the factor k takes into account that a given symbol, for instance A6 in this constellation, can have several symbols at minimum distance. In this case, A6 has 4 symbols at minimum distance, and k is the maximum number of symbols at minimum distance of another one in the constellation. In this case, k will be equal to 4 symbols, because there are symbols in this constellation with 4 symbols at minimum distance. There are others, for instance A0, that only has 2 at minimum distance, but the important is the maximum number of symbols at minimum distance of another one. For this constellation, k is equal to 4. The approximation of the probability of error can be higher or lower than the real probability of error, and in some cases it is interesting to guarantee a minimum performance, to guarantee that the probability of error is below a given threshold, and in this case bounds are useful, because we can obtain bounds of the probability of error to guarantee that the probability of error is below this bound. And there are several bounds. A usual bound is the union bound, and another bound is the loose bound. The bounds can be tight or loose, taking into account the real difference between the value of the bound and the real probability of error. For instance, the union bound is a tight bound because in this picture we have the real probability of error in blue as a function of the mean energy per symbol divided by n0 in decibels, and in red we have the bound that is established by the union bound for a given constellation. And we can see that especially for high values of ES divided by n0, the bound is really close to the real probability of error. This is a tight bound. Then there are other bounds, as the loose bound, that are loose. The difference between the real probability of error in blue and the bound in red in this case is higher in this case. But in any case, this bound is useful because we can guarantee with this bound that the error probability is below it. And this can be useful in many cases.